Let's talk about this. I'm going to record this because we've got at least 2 people out. All right, so let's talk about kinematics. Kinematics is the study of what? Motion, yes. The study of motion. Now, we started with kinematics, so it is without regard to forces. When we talked about kinematics, it was before we talked about forces. Once Newton came into play, kinematics is just sort of a sidelined add-on, isn't it? All right, so we are just literally dealing, when we talk about kinematics, talking about a change in x, a velocity or y, and an acceleration. Those are the big things, aren't they? Now, revolution. There's a difference between a revolution and a rotation. Look at the examples of revolution versus the examples of rotation. In revolution, it says a roller coaster going around a loop, the Earth orbiting around the sun, versus a rotation where it's a wheel spinning or the rotation of the Earth about its own axis.
So would it be based on the positioning of the circle? So say, like the example of the CD, the revolution would be the outside, while the rotation would be the inside?
It has to do with the position of the axis and the object. If you're talking about a revolution, the axis is outside the object. Yeah, and the object is rotating around, like say the Earth is out there, the sun's here. The axis is not inside the Earth. It's a separate object rotating about something else, isn't it? So that's what a revolution is. Versus a rotation, where is the axis? In the object. So a CD or that turntable would be rotating, whereas, and this is the way I always like to say it is. All right, so I am the Earth. I am revolving. I am the Earth. In reality, I'm revolving, and I'm going to get dizzy and fall over, so we're going to stop that. I don't do circles well. So, but you see the difference. The Earth actually does both in 2 separate ways. So, a revolution is circular motion. About an external axis, right? So we've got the sun, and we've got the Earth going here, okay? If you want to think about it, if you were throwing something, if you were rotating something on the end of a string around your head, that would be revolving, not rotating, okay? Rotation, however, is circular motion about an internal axis, yes.
So technically a revolver would be rotating?
Yes. The cylinder on a revolver would be rotating. Yes.
I just thought of that because that's where I go to. I'm like,
No, I think it's great. Irony. Definition of irony. Yes. Okay. So it's an internal thing. Now it says describe kinematic quantities in rotational motion and relate them to linear motion. Okay, so we've got to relate this to linear motion. So what we know is if we've got something starting here, and here's my center, this is at time 0. My little whatever it is right here. Now, after so much time, and it revolves, this thing is going to go and move over to here. Okay? Then the amount it moves, guys, this is an angle theta. It's not an x, it's a theta, isn't it? Now what I want you to think about is this. Here's your picture of that. This guy, Mr. Popsicle, as he rotates to here, this is an angle, isn't it? Mm-hmm. As a matter of fact, all of these, when they rotate around this position here, they all rotate the same
Angle.
degree, don't they? However, they do not all travel the same distance. And we're going to look at the equation that tells you that. They all have the same angle of rotation, they just don't have the same displacement. Okay? They have the same angular displacement, but not the same linear displacement. As a matter of fact, as you can see, the ice cream cone versus Mr. Fry versus the popsicle, the further out you are, the
Further
you travel. Right? Think about it. What are your experiences on a merry-go-round? Where's the most fun to be? On the outside edge. And we'll learn why that is. Because you go faster. If you watch this and keep your eye on these guys, who's got the fastest velocity? The outside does, doesn't it? Yeah. Mr. Popsicle does. He's having the most fun. All right.
My eyes are not happy.
Yes.
Because
And the most dizzy.
that's because when you're in the middle, you're not having to travel as far. So
Yeah. You go the same time. It takes the same amount of time because they're all connected along this line, aren't they? They're going the same amount of time to go that same distance, or that same angle measure. Well, this guy goes further in that same amount of time. So if you go further in the same amount of time, you go faster.
I like the option was to
Yep.
be on a track is the inside.
Yep. Because you don't have to go as fast, or if you go just as fast as everybody else, you actually get ahead of them, don't you?
You have different starting positions.
Yep. In the track.
Have different starting positions and different ending positions.
Yep. Otherwise, it's not fair. That's why they make people like, if you've ever watched speed skating, that's why they make the speed skaters swap positions in the middle of the race. You have to swap out because then everybody gets, and that's why also in races, like when you start racing, even if you're all the way across and staggered, everybody tries for the inside track, don't they? Because it's the shortest distance. All right, so units of angular displacement are what we call radians, not degrees. They are radians, and we all, of course, know that there are 2 pi radians in how many degrees? Yep, 360 degrees, or usually we say pi radians, RAD, is 180 degrees, and we use this for our unit conversion, right? Because it has to be in radians, not revolutions. 1 revolution is equal to 2 pi radians. You might need to know that one. Now, the relationship between linear distance and angular displacement. This is where your arc length formula comes in. And I don't like D here. I like to make this S, because that's what we use in math. S. That's that distance right there. It is part of the circumference, isn't it? So it is dependent on the radius. S is equal to R theta. This is why the further out you get, the more distance you cover, right? Because that is a direct proportion. As R goes up, S goes up, doesn't it? Uh-oh. 1 moment for what? No, I don't want anything. Thank you.
Something.
So will we, so when we use this formula, will we input it into as radians?
Yes. Yes, you would. Not revolutions, not degrees, radians. Okay? So as R goes up, S goes up. Now S is in, the units for S are meters. Because it is a physical distance, isn't it? Put it in the tray over there. Just put it in the black tray or the orange tray. I don't care which tray. All right? Now, what do we know? This is linear displacement, so it's in meters. It's equal to R times the angular displacement. And remember what we said. The angular displacement is the same for all of them. In other words, the disk is fixed. If one point on the disk moves 90 degrees, then all points on the disk move 90 degrees. However, R is not the same for all of the objects on the disk. The further out on the disk they get, the bigger R gets, so the bigger the arc length they describe as they move through that angle.
Teacher, it's our planning.
Yeah. Okay, so is everybody good with this? Remember this, because this is an important one. S equals R theta. You're going to see this pattern quite a bit. So let's move on to looking at what we need to do. Let's solve a problem. This is, after all, physics class. Hipster spins a vinyl copy of an album you've probably never heard of. Pink Floyd's Dark Side of the Moon. And on their vintage record player, the record spins 10 times. Okay? Find the angular displacement of the record in that time. So we are looking for angular displacement, so we're talking about theta, aren't we? So what we're looking for is 10 times 1 displacement, right? Well, what would describe 1 displacement? No. 1 angular displacement. Angular displacement 1 time around is how many radians? 2 pi. So it would be 10 times 2 pi. So theta would be 20 pi radians. And radians, by the way, are unitless. Sometimes you don't even see radians written.
So
It'd just be 20 pi.
that's the answer.
Yeah. That's the answer.
Units are
Yes, actually, while the record was spinning, a fly stands on the record 10 centimeters from the center. So what is that giving me? Ah, that's giving me an R of 0.1 meters, isn't it? Find the length of the fly's path. Now, the length of the fly's path is described by what? That's S. So now we're looking for S equals R theta. R is 0.1, and we found theta, 20 pi. Now this is in meters, so we can go ahead and multiply it out. It would be 2 pi, which would be what? About 6.3, 6.28, 6.3 meters, wouldn't it? Okay. 6.28, 6.3, yeah. Okay. Now, angular velocity, how fast an object is spinning. Again, if I spin that disk over there, every one of those is going to spin the same amount in the same amount of time, isn't it? Because they're all moving the same angular displacement, which means that their velocity, angular velocity, is their angular displacement, which would be delta theta, over time. Well, if delta theta is the same for all of them and time's the same for all of them, then omega, that is, by the way, this is omega, isn't it? Omega is angular velocity. That has got to be the same for all of them. Units of angular velocity are going to be radians per second, or sometimes you just see it as 1 over seconds, or sometimes you just see it as s to the negative 1. Angular velocity, where have we seen s to the negative 1? Hertz. So angular velocity is frequency, isn't it?
So angular velocity will always be the same for all the objects, but linear,
On the disk, yes.
linear velocity is the one that changes.
Yeah. All the linear ones are going to change. All the angular ones are going to stay the same for everything on the same disk. Okay? So the vector direction is going to be the right-hand rule. I described that for you so you can see it. You curl your fingers in the direction of the movement. We know that counterclockwise means that omega is positive, and clockwise means that omega is negative. Because counterclockwise makes my thumb go in the positive direction, and clockwise makes my thumb go in the negative direction, doesn't it? Counterclockwise, right? Actually, this is counterclockwise. Counterclockwise for you guys, positive. Clockwise, negative. And if you think about it looking at a clock looking down, it really makes more sense. Because counterclockwise, your thumb's pointing up. Clockwise, your thumb's pointing down. Okay? Now, what do we know? Relationship between linear speed and angular velocity. V is equal to R omega. Doesn't this look a little familiar? S is equal to R theta. V is equal to R omega. Think there's a pattern there? Yes, there is. So, linear displacement over time versus, say, angular displacement over time, R omega. That's an important one to know. And, of course, the units for this guy are going to be meters per second, right? R is going to give you the meters. Omega is going to give you the per second. Angular acceleration. This is the rate of change of the angular velocity. In other words, that is alpha. Alpha is equal to delta omega over time. Now, the convention. If we have a positive angular velocity, that would be going which direction? Counterclockwise. So if we have a positive angular velocity going counterclockwise, this way, right? Which way do I have to push it for it to go faster?
Down.
Counterclockwise, don't I?
Yeah.
So the acceleration for it to get faster, the acceleration has to go in the same direction. To slow it down, I have to apply it in the clockwise direction, don't I? Now, the right-hand rule still works for this as well. Angular acceleration has to be in the same direction as so it's the right-hand rule for that as well. Clockwise makes it a negative acceleration. Counterclockwise makes it a positive acceleration. Okay?
Is it because if it's attached to a solid object, like say car, if it moves counterclockwise, the car will move forward?
I don't know if that's the convention, but you would think so. Yeah. It's a cross product. It's a math thing. It's a cross product, which basically says that if you have a cross product, it's like this. If you have things crossed this way, then this is the result.
Okay.
And so it makes a lot of sense if you think about it from a car perspective. The wheel is turning, yay, right? Or you can think of it, and that's why you get torque converters, and differentials are all based on changing an axial motion turning this way into a motion going this way. Yeah, you've got it this way to this way. Because if you think about it, your engine, your main drive shaft is going this way. And now you have to change that to going this way to get your tires to go the right direction.
Mm-hmm.
But cars have got a lot of rotational motion in them. All right.
One of my friend's drive shaft fell out from under his car, and he had to call the tow. And he said it didn't cost a lot to fix.
That's good. If you didn't damage it, then it's good.
He just started going up this hill, and all of a sudden you see boom, the car starts sliding back.
Mm-hmm.
So scary.
Units of angular acceleration. What are the units going to be? This is radians per second. So this is going to be radians per second squared, or 1 over second squared, or to the negative 2. Relationship between linear speed and angular velocity. Linear acceleration and angular acceleration, excuse me. A is equal to what? I bet you can guess.
A equals
Okay, but we're looking at patterns we found here. Let's start with the patterns we have found so far. S equals R theta. V equals R omega. So A equals R alpha. Yes.
Why do we use alpha in math when we're doing sine, cosine, and
Because it's an angle.
Fish.
okay.
It's just another angle.
Okay.
Greek letters are usually angles until you get to physics where they mean other things.
Is that not what the Jesus fish comes from?
Yes, alpha and omega. Yes, alpha and omega, yes.
Oh, Omega was like a little line and it was like a thing.
No, that's an ohm.
Oh,
Oh, yeah, that is.
What is that?
It's a W.
Oh, right.
There are lowercase and capital versions of all of them. All right, so let's actually look at what I've actually, whoa, what did I do? This guy, linear kinematics, rotational kinematics. Guess what? Everywhere we have a D, we can instead put, actually in the way we've thought about it is delta X, we can put delta omega. Everywhere we have a V, we can put delta theta. This is theta, excuse me. Everywhere we have a V, we can put an omega. So omega initial T plus 1/2, and instead of A, we put
alpha.
yes. And they're exactly the same. So delta X here. So delta theta equals omega final T minus 1/2 alpha T squared. So if you know the linear kinematics equations, guess what? You know their rotational equivalents. Just substitute in the Greek letters. Yes, literally. So this one becomes omega final squared equals omega initial squared plus 2 alpha delta theta. And this should be delta X. I hate the D. This should be omega final equals omega initial plus alpha T. And then finally, theta equals, average theta, right? Equals omega initial plus omega final divided by 2 times T. And if you look at your purple sheet, you will see that indeed they are on there, most of these. The same ones for kinematics are on there for rotational.
It's that written
2. I'm assuming you mean this. Here. 2.
probably should have looked at the other
T.
side, but
Yeah. It's okay. So now we can apply these the same way we'd normally to rotational motion. So we're starting with kinematics again. Now, the only thing is that everything has to be in radians per second, not revolutions per minute or anything else. So we have to do some unit conversion. If you look at 800 revolutions per minute, so let's change that one out. 800 revolutions per minute. How many in one revolution is what? How many radians? So 2 pi radians. And in 1 minute, there are 60 seconds. So we end up with what? 16 revolutions, minutes. We end up with 1600 pi over 60 radians per second. Get rid of a 0, divide by 2, we get 80 pi over 3 radians per second. Let's do the 500. Same thing, right? 500 revolutions per minute. So we're going to end up multiplying by 2 pi and dividing by 60, right? So we get 1,000 pi over 60 radians per second, which is, drop a 0, divide by 2, we get 50 pi over 3 radians per second. I know I went through that pretty fast, but I'm assuming most of you can do unit conversion between math and physical science and or chemistry.
For the first one, for the 800, you be at 80.
Mm-hmm. Oh, I just left it as 85 over 3. And look, here's the problem. We got 60 revolutions also. So 60 revolutions is what?
2 pi radians per second.
60 times 2 pi, 120 pi radians. Okay? So now we've got everything we need here. We've got omega initial is 50 pi over 3 radians per second. We've got omega final. I'm sorry, this is omega final. This is omega initial because it's 800, right? So it's 80 pi over 3 radians per second. And we have theta, which is 120 pi radians. So those are our givens, aren't they? So now we can actually look at what the question's asking. A, what is the angular acceleration? So we are looking for alpha. So I want you to go up and look at those equations that we have up here and tell me which one we're going to use. 1, 2, 3, 4, or 5. What are we missing here? We don't have time. So can I use 1, 2, 4, or 5? So which one can I use? I can use 3. And that's what we will use. Omega final squared equals omega initial squared plus 2 alpha delta theta. So let's plug in. 50 over 3 pi squared equals 80 over 3 pi squared plus 2 alpha times 120 pi. This is where you can start actually turning this into decimal numbers if you want and make it an equation. Now, should the result be positive or negative? Why negative, Garrison? Because it slows down. So you need to end up with a negative answer, don't you? So get that trusty calculator out and do some calculating. Don't forget to square. You get about negative 5.7 radians per second squared. Okay? About negative 5.7. Yeah. All right, so now part B says how long does it take for it to slow down? So what are we searching for now? Time, so pick an equation. Which one looks the easiest? 4. I think 4 looks the easiest to me. Omega final equals omega initial plus alpha t. This is always our favorite one. It's always the simplest. So this is, move back here. 50 pi over 3 equals 80 pi over 3 plus what? Negative 5.7 t. Solve for t. about 5.5 seconds. And then C says find the linear speed of an object that's 0.35 meters from the center of the wheel that's spinning at 500 revolutions per minute.
So you get
Omega to 500, so
Yep.
we already changed some of those, but
Yep.
it's just,
R omega, right?
it's a negative initial.
That's a mega final. It's 500.
500 was?
Yeah, mega final. It started at 800 and slowed down to 500. It's okay.
I got 5.
So what's R?
0.35.
Yep. Times what? 50 pi over 3. And what do you get? Yeah. About 18.3 meters per second. Okay? What is wrong?
I left my glasses in my friend's car. 50 over 3.
Yeah. 500 revolutions per second or per minute was 50 pi over 3, wasn't it? Times the
Yeah, I did.
Okay.
I know what I did wrong.
Okay. All right, so angular acceleration of a wheel is 4 radians per second squared. How many revolutions does the wheel make in the first 6 seconds if it is initially at rest? So that is omega initial equals 0. This is time, and this is alpha. So what are we looking for? How many revolutions? We got to start with, this is not delta theta, is it? But it's a version of that. So delta theta equals omega initial t plus 1/2 alpha t squared, right? V initial t plus 1/2 at squared, just change it. So we know this is 0, isn't it? So we're going to do 1/2 4 times 6 squared. And delta theta is what? 72 radians. We want to know revolutions. So that is not the answer. Yes. So now we have to do one revolution is what? 2 pi radians. So this time we have to divide by 2 pi.
Like
11.5 revolutions. So really, we're really talking about 11 full. Yeah. No. Okay. My guess is this. You plugged in 72 divided by 2. You did it just like this. You better put in parentheses. Otherwise, you divided by 2 and multiplied by pi.
There we go, yeah.
All right. A wheel is rotating at 4 radians per second. You know what? We've got like 1 minute. We're going to stop right here. We can't finish this last complete one, but you guys get the idea. If you can do kinematics, you can do rotational stuff. What are the tricky things? Make sure you're in the right units. Make sure you're not in revolutions. Make sure you're in radians per second. Make sure you know how to convert between linear and rotational, right? Okay, those are the biggies. If you'll notice up there, it says make sure you turn in your lab. I'll take it first thing in the morning, but no later than first thing in the morning if you didn't turn it in today.
I was looking through the 6.1 practice exercises, and the
Uh-huh.
first one was is it circular or rotational? Circular
same thing as revolution? Is it circular motion?
Is it? Yeah.
Okay. I just wanted to make sure, because it was asking if the Earth rotating around the sun was either rotational or circular.
Oh, Mint's revolution. Yeah.
It means revolution.
Yeah. Is it revolution or a rotation? It's a revolution.
So circular. Is,
Yeah.
okay.
All right, guys.